So far in previous videos, we've been talking about using Arduino with variables to store values. But as you might notice, every time we do a power cycle or reset the Arduino board, the variables go back to the default value. If you want to store a value permanently, we use a memory inside the Arduino board called EEPROM that can be very useful for things like saving user settings and remembering the state of a variable. There are a few things you need to consider about using the EEPROM. First is that you should not write that memory too often because it has a limited amount of writes that you can perform, around 100,000 write cycles. That's plenty for a project, so normally you will not really have to worry about this. But the reason to take this into account is that you should only write the EEPROM when you really need to. For example, if you were to write every cycle of the loop, you will wear out the EEPROM in just a few days, since the loop usually runs many times per second. Instead, it's better to write the EEPROM only when needed, like when pressing a button or something like that. The other thing to consider is that the way it works is by recording bytes of data, each on their own address. The typical Arduino Uno and Arduino Nano can store up to 1024 bytes. The basic way EEPROM works is selecting the address you want to read and then choosing where you want to store that value. That in this case is called variable 1. We do the same when writing, selecting the address and then the variable that has the value you want to store into the EEPROM. In this example, we increase the value by 1 before writing, so after a power cycle, it reads, increases by 1, and then writes it back. This allows Arduino to know in what value it was left and continues doing this process even after a power cycle. But remember that each address is only 1 byte, and a byte can only store values from 0 to 255. So when we write variables to the EEPROM that uses more bytes, keep in mind that it's going to use that amount of bytes. To make it easier to understand, let's overview the most common types of variables with this example sketch. So far in this tutorial series, we've been using the integer, expressed as int, which can store values from -32,768 to 32,767. But there are many other types of variables that we can use, each one with their own limitations and the amount of memory they use. One of the simplest ones is the byte, that, like the name implies, it uses only 1 byte. Although that means it can store a very low range of values from 0 to 255. If you were to try putting a higher value, it will overflow and start over from 0. For example, if we put the value 260 into a byte, it's actually going to store the value 4. To store higher values, we need to use a variable with more bytes, like the integer that uses 2 bytes, and it can store a large range of numbers, including negative numbers. Since it has a good balance between a wide range of values and only uses 2 bytes, it's a very popular variable used in many projects. In case we want to store higher values and we don't care about negative numbers, we can use an unsigned integer that instead of allowing negative numbers, it doubles the positive values we can hold. Remember that in this part of the sketch, we are just creating different types of variables with their name and value, just to show how they work. Later, I'll show how to store them into the EEPROM. The next most common variable to store higher values is the long, which uses 4 bytes and the range of values is much higher, including negative numbers. Like the integer, we can also add the word unsigned to double the amount of positive values, with the trade-off that it cannot store negative values. There are variables that store even bigger numbers, but they are harder to use, so we are not going to deal with them in this tutorial. For now, let's continue going through the most popular variables. This one in particular, called float, is very interesting. The main feature is that it has a decimal point to allow saving fractional numbers. But this comes with some complications. For example, they don't store precise values. Instead, they store approximations. That's why you should not use them in mathematical operations or anything like that, because they can give weird results. I'm not going to cover the reasons for this behavior on this video because it's a big subject. But all you need to know is that you should only use 6 digits if you want to keep it precise. And you should not use them for any math operation. What I do in cases I need to use float variables, for example with very accurate temperature sensors that give the temperature with fractions, the best thing is to convert them into a normal variable, do all the operations we want to do with it, and then convert them back into a float at the end when we're ready to print it in the serial monitor or display. Continuing with the other variables, we have the character, expressed as char, that can store a wide range of letters, numbers, and symbols, and it uses 1 byte. Characters are great, but to store words and longer text, we use what we call a character array that joins multiple characters to create a string. When we create character arrays, the number inside the brackets specify the amount of characters it can store, but you should always add an additional one to terminate the string. For example, here I created a character array of 6 characters, but we can only store a maximum of 5 characters in there. This only applies to character arrays because basically we're creating a string that is a sequence of characters, and we need that extra character to terminate the string. We can create arrays of any variable really, but for now let's just continue. The idea behind choosing the type of variable to use is to avoid wasting memory selecting variables that take too many bytes unnecessarily, but prevent choosing variables that don't have enough memory to store the values we want to store. Generally, this is not very important because Arduino boards have enough memory for most common projects. But for the EEPROM, this is very relevant since each address is only 1 byte, and we need to consider the amount of bytes each variable takes to know what addresses we are actually using. Let me show you in this example. So we created 2 variables of each type. One is to write the EEPROM and the other one to read the EEPROM. Let's start with the byte, which is straightforward. We select what address we want to use and the variable to write into the EEPROM, or to store what we read from the EEPROM depending what you want to do. Choose the command put to write and the command get to read. In this example, if you want to keep the data intact, you should not write that address 0 with any other data that is not intended to be there. So in the next item, we now use the address 1. We can use any address really. It doesn't need to be in sequence, but for this example, I choose address 1. We do the same. First write the data into the address 1 of the EEPROM. But since we are writing an integer which uses 2 bytes, this means we are not only using address 1, but we are also automatically using address 2. So when we want to store another variable like this unsigned integer, we should not use address 0, 1, nor 2, because we are already using them. The next address available is 3, so I choose that. Again, it doesn't have to be in sequence, but for this example, I choose that. Any value between 0 and 1023 is a valid address. Same thing happens with the unsigned integer, that even though we choose address 3, it's going to use address 3 and 4, because unsigned integers uses 2 bytes. And so on with the rest of the variables. Long uses 4 bytes. Same for unsigned long. Also with the float. In the case of the character, it only uses 1 byte. But for the character array, this is more complicated because we need to store each character on a different address. The array has 6 characters, so we write each address with each character. There are better ways to do this, but I show it like this to make it clear what we are doing. Same when we are reading the EEPROM. We read each address and store the result in the corresponding part of the array. The result is writing all this data to the EEPROM and reading it to be printed in the serial monitor. If you want to simplify things, just use addresses that are far apart from each other to make sure to not overwrite bytes that you are using for other things. Let's say you store one integer in address 0. Then you could use for another variable the address 10, and then maybe address 20, and so on. That way you can be sure there's enough space between them to avoid a conflict. I invite you to experiment with this, and when you feel ready, watch the next video that is going to be about some ways we can jump to specific parts of the code while executing. Very useful for creating loops and having isolated codes that run only when called. I hope it was helpful and see you in the next video. Bye bye.